Main goal for today, guys, is we're going to be talking about the linear regression line, okay, in correlation with the linear regression line. So you will be able to calculate the correlational coefficient of a data set and write the equation of the line of best fit by completing problems as taught. So we're learning two things with this lesson. We are learning how to calculate the correlational coefficient of a data set. So we're going to learn how to calculate R, okay? And we're going to write the equation of the line of best fit. So we're going to actually be able to write the equation of line of best fit, okay? So remember that correlation, right, is all about how two variables or two sets of variables relate to each other, how they connect or how they move with each other. So over here, right, we have 100% of the variation of variable A, 100% of the variation of variable B, sorry. And there's no overlap between the two variables, okay, which means there's no relationship. We have no correlation here. There's seriously there's no relationship happening between the two variables, right? It's essentially like a function. That's what it's getting at, okay? When you have some overlap between the variables, some relationship there, okay, then you have a somewhat of a correlation. It has some relationship, okay? When you have a lot of overlap between the two variables, then you have a stronger relationship or a stronger correlation, okay? Now remember again, correlation does not mean causation. Just because two variables are correlated does not mean that one causes the other, okay? It just means that there is some sort of a relationship between them. So let's talk about the line of best fit, okay? The line of best fit is a line to describe and predict values of data using the method of least squared. A line to describe and predict values of data using the method of least squared. So the method of least squares is that the sum of the squares of the difference between the data and the line, okay? Between data and the line. So the method of least squares is when the sum of the squares of the difference between the data and the line is minimized. So the smaller this number, the better. Okay, you are essentially looking at how much does the real data differ from the prediction that your line is giving you, that your line of best fit is giving you. You're looking at the difference between your real data and your predicted data. You're looking at the difference between your real data and your predicted data. So what we do is we take the real, we subtract it from the predicted, we square that, and then we add all of them together. Okay. This is also called the regression line or the line of least squares. It is also called the regression line or the line of least squares. Okay. Some properties of a line of best fit here is that there's only one line of best fit for any given data set. So there's only one line that has the smallest error, it's called, okay? So there's only one line that has the smallest, least squares, and that's gonna be your line of best fit. Okay, you can have other lines on there, but they're not gonna be the line of best fit. The line of best fit contains the center of mass, meaning it contains the coordinates that are the mean of their respective variables. So the line contains the x mean and the y mean. Oh, that looks like x midpoint, y midpoint. Hold on, that's really bad notation. Don't write that. There's better notation for this, guys. And I should know it. It contains this point right here. The mean of the x's, comma, the mean of the y. So where the x's come from, that's one of your variables, right, that you're comparing. And the mean of the y's are the other variable you're comparing it to, right? So you're looking at the two sets of variables that you're comparing. And the property and the line of best fit can also compute the slope and the y-intercept from the data points. So you can actually compute the slope and the y-intercept from your data points using your line of best fit. Okay. So line of best fit, there's only one. It contains your x mean comma y mean point, and you can compute your slope and your y-intercept based on your data points. Okay. So let's take a look here. Correlation coefficient. Okay, the correlational coefficient is a measure of strength of the linear relationship between two variables. It is denoted with R. Okay? And we kind of already know that from our 2.2 where we were looking at a visual correlational coefficient. Okay, it is a value that describes the fit and the direction of the line. It is a value that describes the fit and the direction of the line. So fit meaning how tight your dots are, right? That's the fit. If you guys remember from 2.2, right? Let me pull that out. Okay, we're talking about this situation here, right? The fit meaning how tightly your data points fit together or how widespread they are, right? And the direction, where to go? The direction of the line, meaning is it a positive line? Is it a negative line? Okay. Now, the greater the absolute value of R, so we look at the absolute value of R when we're looking at the strength of the correlation, right? So the positivity and negativity is solely there to give us whether our line is going in the positive direction or in the negative direction. But it's the absolute value of R, that value of R, right, that tells us the strength of the correlation. So the greater the absolute value of R, the greater the correlation. Okay, since the absolute value of R equals 1 is a perfect correlation, the absolute value of R will never be greater than 1. Okay, with AKA the absolute value of R is either going to be less than or equal to 1 or greater than or equal to 0. Okay, so just a little review from the previous lesson there. And I'll give you guys 30 more seconds to finish writing down anything you need to write down here. And then I'm going to flip over the page. Okay, we are going to do some examples for finding using the method of least squares and so on. Okay, and calculating the correlational coefficient. Oh boy. All right, so you will need your graphing calculators just because it's going to be a lot of calculation. Okay, so make sure you get those out, graphing calculators here. We will be doing a lot of calculations, okay? All right. So let's take a look at this example up top. Okay. It says a national consumer magazine reported the following correlations. The correlation between car weight and car reliability is negative 0.3. The correlation between car weight and annual maintenance cost is 0.2. Which of the following statements are true? Heavier cars tend to be less reliable. Heavier cars tend to cost more to maintain. Car weight is related more strongly to reliability than to the maintenance cost. Which of the following statements is true based on those? So I want you guys to, in the chat, give me a 1, 2, or 3 based on what you choose privately. I want a private answer. Okay, send it only to me. And I'm looking for participation from everyone. Okay. So I have a lot of 2s and 3s. I got a few more 2s. Okay. Some people are having a difficulty with the instruction of privately, but that's okay. So I had one person say 1. Heavier cars tend to be less reliable. Okay, so that's pertaining to the car weight and the car reliability. Okay. Juan, can you tell us why you chose that one?
Well, I chose it because it sounded like the right answer, but then I remembered he said something about like the smaller being the better, and then yeah.
Oh no, for correlational coefficients, the bigger the better. We're talking about R here, right? We're talking about R. That's what our correlation is, R. So with R, the bigger the better. Okay.
Okay.
All right, let's see. For my kids that chose 2, let's hear from Ariana. Why did you choose 2? Heavier cars tend to cost more to maintain.
I chose 2 from the second book where it says the correlation between car weight and annual maintenance costs 0.20. And
Okay,
that's why
so you thought
I
that that
chose 2.
translated to heavier cars tend to cost more to maintain?
Yeah.
Okay, okay. And then let's see, I had a few people choose 3. Um, Zon, can you tell us why you chose 3? Car weight is related more strongly to reliability than to maintenance cost. Zon?
I said it because it looks like the correlation to car weight and annual maintenance is larger than the car weight and reliability.
Okay. Thank you. Let me ask you guys a question. Heavier cars tend to be less reliable. Is that what this is saying? That with car weight and car reliability, that heavier cars, so all heavier cars are less reliable? Or not all, but most? Okay, and then this one says heavier cars tend to cost more to maintain. Okay, the correlation between car weight and annual maintenance is only 0.2. What does 0.2 mean for R? Is that a strong correlation? Is that a some correlation, or is that a weak correlation? Look at these numbers, right? Are these strong correlations, some correlations, or weak correlations? These are weak correlations. Yeah, these are weak correlations, which means this whole statement of heavier cars tend to be less reliable, this is saying it as if there was a very strong correlation, right? But these are very weak correlations, especially this one. So these tend to cost more, tend to be less reliable. You're really going off of a very weak correlation here, which means making a statement like this is it's irresponsible to a certain extent, right? It's like serving 30 kids, and out of the 30 kids, 2 kids said that they loved having boba after school, and then taking that and saying high school students tend to love to get boba after school. Is that based on a strong data? No. Right? So the only thing that we can say for a fact, the only thing that we can say to be true is that the car weight is related more strongly because it's a 0.3 versus a 0.2, right? The car weight is related more strongly to reliability than to maintenance of cost. That's the only statement that can be true here. Because that's the only one that's based on the given information that we can say for sure. Okay, so the 2 or 3 of you that chose 3, good. And then the rest of you guys, it's a very easy trick to fall in, because you want to look at these correlations and you're saying there's some correlation, but it's a very weak correlation. So you really have to pay attention to the strength of the correlation before you can make statements like tends to or usually or anything like that. Okay. All right.
Why does it say R off to the side?
Because I was pointing out to Juan that correlation, we're talking about R. He thought we were talking about least squares.
No, I'm talking about on the sidebar.
Oh, same reason. I just wrote it in 2 places. Yeah. Same reason. Okay. So now we're going to take a look at the process of calculating the correlational coefficient. So let's pay attention, okay? So R, there's a sample formula and then there's a population formula. And the main difference is in the sample, we use n-1 and we use the sample standard deviation. Versus population, we use n and we use the population standard deviation. So we use sigma. Okay. So same difference essentially in sample versus population. It's usually that n-1, right? So there's a process to calculating your correlational coefficient, guys. So let's make sure we understand all of the different parts here. Okay, in our sample, our correlational coefficient R will equal 1 over n-1. Okay, n, right, is your number of data values. Sorry, I'll move my hand in a second. I'm just holding down my paper so I could write. Okay, n is equal to the number of data values. That's what our n is. So 1 over n-1 times the summation, right, of 1 to n, so all of our data points, of each x value subtracted by the mean of x divided by the standard deviation. So each one of these times its y value minus the y mean divided by the y standard deviation. So our standard deviation, S sub x, is our standard deviation for x. S sub y is our standard deviation for y. Okay. Now for population, it's very similar. Instead of n-1, we have n, so 1 over n. And again, we have summation of, so our x minus the mean of x, so mu of x, divided by the standard deviation of x. Okay. And then y minus the mean of y divided by the standard deviation of y. Okay. So if we need a reminder, which I think we do, of the equation for standard deviation. So we're going to put that right over here on the side. Okay. So our standard deviation, I'm going to do the sample one. Okay. First. So that's going to be the square root of the summation of x minus x bar squared divided by n-1, which means that our standard deviation for y will equal the square root of y minus y bar squared divided by n-1. Okay. The only thing that changes here for our sigma, so sigma of x, right? This is for the population. Only thing that changes, oh wait. Mu of x squared divided by n. And then standard deviation of y is going to be y minus mu of y squared divided by n. Okay. So what this means is that it means we are going to be, calculating a lot of minor things in order to bring it back and do a final calculation here. And so having a grid to help us out really helps. Okay. So we're going to need to, in order to calculate our standard, our correlation coefficient, we're going to need to first find the means, okay, because we need those. We need to find the means because the mean is used in both our standard deviations and the formula here, okay? So we're going to need the mean for either one. And then we're going to need to calculate each of their standard deviations. So we're going to need that x minus x bar or that y minus y bar because that's also used in our standard deviations. Okay. Oh, I forgot the summation here. My bad. I knew something was missing. I was like, there's something missing. I forgot the summation in these standard deviation things. My bad. All right. So we're going to have to do a lot of minor calculations to get to the final big calculation. That's what I'm trying to get at here. And usually we use the sample because calculating a correlation coefficient, you have collected a set of data, and usually that data is not the whole population. Usually you've collected data from a sample population. So most of the time we're using sample, not population, okay? Because again, it's impossible for us to collect data, real data, right, on an entire population unless we actually have. So like if we're doing something that's for the class, right, related for the class, and we've collected data on everyone from that class, then yeah, we could use population. But even if one person was absent during that collection of data, then we won't be using, we would not be using the population. We would have to use the sample. All right. So we're going to calculate the correlational coefficient for the data set below, and then we're going to interpret the correlational coefficient. Okay. So first things first, we're given 1, 1, 2, 3, 4, 5, and 5, 7. So we're only doing it with 4 points right now. Okay. The first thing we need to do is we need to calculate the x bar and the y bar. So our x mean and our y mean, right? So we do that. My x's is a 1, a 2, a 4, and a 5. I have them right over here. My y's are 1, 3, 5, and 7. So we can make this easy for ourselves. Add these guys up. 1 plus 2 plus 4 plus 5. Okay, so I'm going to do this just so that we have space to work, right? So we're calculating our x bar. It's going to be 1 plus 2 plus 4 plus 5. And divide that by the number of data values there, which is 4. Okay, that gives us 12 divided by 4, which is 3. That means our x bar is 3. Okay. All right. And then we can do the same thing for our y here. Okay, so y bar, I have 1 plus 3 plus 5 plus 7. So 1 plus 3 plus 5 plus 7 divided by 4. Okay, that's going to be 16 divided by 4, which is 4. So my y bar is 4. Okay. Are we okay so far? We're doing okay? Sticking with it? Okay. Now we're going to take each data point and we're going to subtract it from the mean that we found. So this is going to be 1 minus 3. This is going to be 2 minus 3, 4 minus 3, 5 minus 3, right? So this will be negative 2. This will be negative 1. This is just going to be 1. This will be 2. Okay. All right. So then we do the same thing for the y's, right? So we're just trying to move up quickly through. So this is going to be 1 minus 4 and so on. So 1 minus 4 is negative 3. 3 minus 4 is negative 1. 5 minus 4 is 1. 7 minus 4 is 3. Okay, so that's how we get those values. We're just subtracting. Okay. Now for the next one, we need to divide it by the standard deviation. So now I need to know what the standard deviation for x is and the standard deviation for the y is. Okay. Well, our standard deviations use these values where we have the data minus the mean, right? That's part of the equation up here. That's part of that equation. So when we do our standard deviation, okay, so I'm going to do my S sub x here, okay, I already have my values subtracted. So really it's just, and then it's I'm squaring them, right? So it's whatever the data point minus the mean is squared. So, and then summation of all of them. So it's going to be, I have the data point minus the mean, that's -2. So it's going to be -2 squared plus -1 squared plus 1 squared plus 2 squared. Okay, so each of the differences squared and added together, divided by, we're doing the sample here, right? Because I don't know if that's the whole population. That does sure as heck does not look like the whole population. So we're doing the sample here. Okay, so that's going to be n minus 1. So it'll be over 4 minus 1. So then we just go through and we simplify as we go. So this is going to be 4 plus 1 plus 1 plus 4 divided by 3. Okay, well, 4 plus 4 is 8 plus 1 and 1, that's 10 divided by 3. So the square root, so then I take my calculator, which I don't know where I put. Okay, and so we're going to do the square root. That's right above the x squared there. So we're going to do the square root of parentheses 10 divided by 3. I'm not even messing with the decimals. I'm literally just putting the fraction in there. Equals 1.8257, yada, yada, yada. I'm just going to round to the hundreds place for my own sanity here. So we're going to put this as approximately 1.83 because it was a 1.8257, so 1.83. Okay, so that means that my standard deviation here
Can you
is
move it?
1.83. Say that one more time, Kelly.
Can you move it down so we could see the rest of it?
There you go. Is that good?
Yeah.
Okay. So all I did was, so this was like a double thing, right? Finding the x minus x bar and the y minus y bar. It's like a double thing for me. So because I can use, I'm using this here for the correlation coefficient, but I'm also using it in finding the standard deviation, right? So it helps me in two places there. So then all you do here is now x minus x bar. So this quantity here, you're just going to divide by your standard deviation of x, so 1.83. So I'm going to take each one of these quantities here, and I'm going to divide it by 1.83. Okay, so I will have -2, oops, -2 divided by 1.83. Okay, I'm gonna just put it all in my calculator and then we can write it. -1 divided by 1.83, and then 1 divided by 1.83, and then 2 divided by 1.83. I mean, these repeat essentially, right? And so you get this situation happening here. So again, for these, you can, again, round to the hundredths place. Okay, so starting from there, -2 divided by the 1.83, that gives me a -1.0928, so -1.09. And so that's going to go here, 1.09, right? If you guys want, you can write exactly what we're doing here. You don't have to erase it if you know exactly what we're doing, but essentially what we did is this, right? Which is our -1.09. And then over here we have -1 divided by 1.83, which is our -0.55, because it's a 5, 4, 6. So round that 6 to a 5, or that 4 to a 5. And then again, 1 divided by 1.83. Now it's just going to be positive 0.55. And then lastly, our +2 divided by the 1.83, which will be our 1.09 positive. Okay, so we have the x's. And now we're going to do y's. So we're going to do the same process for finding the standard deviation for the y's now, okay? We have our y minus y bar, or y minus the average y. Okay, we have these values right here. So we're going to use them to find the standard deviation of the y now. And again, we have standard deviation of the y. Okay, big square root. Take each one of these differences and square them, add them together. So I have -3 squared plus -1 squared plus 1 squared plus 3 squared. Okay, divided by, once more, 4 minus 1. And we simplify. Okay, so this will be 9 plus 1 plus 1 plus 9. Right, I'm just squaring each one of these. And then divided by 3. Okay, these guys added together at the top is going to give you 20 divided by 3. So once again, you take your calculator, you have the square root. So square, oh, hold on. Yeah, square root is right above the x squared in blue. So you're going to do second and then hit the x squared. Okay, second is whatever's in blue. Okay, so then you have parentheses. I'm going to put parentheses 20 divided by 3 so that all of that is under the radical. Enter. So this gives me a 2.581988, so on, so on. So that's going to be a 2.58. Okay, so our standard deviation, our standard deviation for y is a 2.58. Which means that each of my y's now for the next column over will be divided by 2.58, and that'll be my next column there. Okay. If I can move it over just a tad here and we can work through that. So this is going to be -3 divided by 2.58 and so on, right? So -3 divided by 2.58 is -1.1627, so 1.16, and then we have -1 divided by 2.58, and that's going to be a -0.387, so that'll be a 3.9. Okay. And then, of course, these are just the positive versions of these. So this will be 0.39, and this will just be 1.16, right? And our data just worked out that way. It's not always going to be that. So now that you have the values of your x's, I'm going to move right up here, right? Now that you have the x values and the y values, right, from each of these parentheses, you are now going to multiply them together because it's the summation of their product. It's the summation of each of the data sets product, right, of the x's and the y's. And so you're literally going to take this, right? So you're taking the value for your x minus x bar divided by standard deviation of x times y minus y bar divided by standard deviation of y. So for each data point, right, notice it was like 1, 1, it was matching, 2, 3, it was matching, 4, 5, it was matching, 5, 7, it was matching, right? So for each of these data points, you are just going to multiply that guy to that guy there to get this. And so you just do -1.09 times -1.16, and that will be 1.2644. Because this is not a continuous along decimal, I'm going to write the whole thing. Okay, 0.55, so -0.55 times -0.39. Please make sure your zeros are in the proper places. So this is going to be 0.2145. Okay, and then this is the same exact multiplication. So I can even put a 0 there, 0.2145. And then this times this is exactly going to be that. So 1.2644. Okay, I'll give you guys a second to finish writing those down. Okay. So now the whole process of finding your correlation coefficient is to add each product, right? So it's the summation of the products times the 1 over n minus 1. So the final step here is going to be to find r. We are going to do 1 over n minus 1, which is 4 minus 1, times the summation of all of this. So 1.2644 plus 0.2145 plus 0.2145 plus, I'm running out of space here, 1.2644. And then of course we just add and divide essentially. So this is going to be, and you can even make it like you can do 2 times each of these and 2 times each of these, but it's really just up to you. You can 1.2644 plus 0.2145 plus 0.2145 plus 1.2644 divided by, essentially that's 3, right? And that gives us 0.92. So our value here, we could even write the steps here. So this becomes 2.76475 divided by 3, which is approximately 0.92 because of that guy, right? Did I do something wrong here? Did I input something incorrectly? Let me try this. 1.2644 plus 0.2145 plus 0.2145 plus 1.2644. Oh, I got a different number. Hold on. No one's correcting me, eh? Thanks a lot, guys.
It's because we couldn't really see it because it's not moved down on the paper.
What do you mean?
You can only see the top part.
On my screen, I can see the bottom part.
Well, on our screens, we can't.
Well, then you gotta speak up. Thank you for speaking up. You guys gotta communicate with me. Okay. So this then, so these added together, right, give you the 2.9578 divided by your 3 from the 1 divided by 4 minus 1. Okay. And so that gives you an approximate of 0.9859, which we're going to say then that our R is equal to 0.99. Okay. So our R is positive, which means this is a positive correlation. And as far as 0.99, what kind of correlation is that? What's the strength level? Do we have a weak, a some, a strong, a very strong?
It's very strong.
It's a very strong, yeah. I would call this a very strong positive correlation. Okay, I would call that a very strong positive correlation. Very good, guys. So it's a process, but it's not a difficult process. Okay, it's just a long process. right? That's the main difference there. It's not a difficult process, it's a long process. Okay. All right. So I want you guys, there's another example on the back. Okay. And I want you guys to grapple with it. I want you guys to go through the process. Oh. Over to that side. Oh, that's unfortunate. Okay. All right. I want you guys to struggle with this. I'm going to give you, it's 9:48. Okay. I'm going to give you guys starting 15 minutes and then we'll check in. Okay. So 15 minutes and then I'm checking in. The hope is that you can get most of it done in 15 minutes. Okay. Any questions? Okay. So I'm going to mute myself. Okay. All right, Kelly, I was saying you guys have 15 minutes to work on this example here. So suppose 5 students were asked their high school GPA and their college GPA. We want to know if high school and college GPA are related according to this data. And if they are related, how can I use the high school GPA to predict college GPA? Okay, so you have your high school GPA, you have your college GPA. Okay, let's say this is our X and this is our Y. Okay, for the sake of discussion. All right, so 15 minutes on the clock, guys. All right, ladies and gentlemen, how far have we gotten here? Okay, do me a favor in the chat, write down how many more minutes you think you need, and I will try to average. Okay, so based on responses, I'm gonna give you guys 5 more minutes, all right? So those of you that are done, you can check your work as I'm completing the work. And those of you that are still working, you can just double check to see if some of the answers that you have gotten are correct, like the means and the standard deviations, okay? So I'll give you guys 5 more minutes to work. All right, ladies and gentlemen, the timer went off, but I did not hear it. Anyway, so we should have gotten a correlation of approximately 0.95, which means we have a strong positive correlation. Okay, can you guys give me a thumbs up if that's what you got, or a thumbs down if that is not what you have? Some sort of response in the participants section, I would appreciate. Okay, good. Waiting for responses from Zahn, Will, Lumeria, and Kelly. If you're not done, let me know in the chat so that I know that you're not just ignoring me. Okay, so we did have some questions that we wanted answered though, right? It says, we want to know if high school and college GPA are related according to this data. And if they are related, how can I use the high school GPA to predict the college GPA? So we can see that there's a strong positive correlation, right? Which means we can say that high school GPA, high school GPA and college GPA are or have a strong positive correlation. Okay, which means high school students with high GPAs are more likely, right? We don't want to say will get, but we want to say are more likely to have similar college GPAs. Okay, they're more likely to have similar college GPAs. All right. The next is finding the line of best fit. Okay, finding the line of best fit has its own formula that we need to be able to use. And it is all based on the X's and the Y's. Luckily for us, we're not really finding any means or standard deviations, but it does require some summations, right? So when we take a look at finding the line of best fit here, okay, I'm trying to rush because we only have about 6 minutes left here, guys. I'm sorry. When we're trying to find the line of best fit, the equation itself is y equals ax plus b, right? So that's pretty much mx plus b, right? But to find a, we use summations of my x's and my y's. So pay attention to the different summations. Okay, you have the summation of xy, which means it's literally x1 times y1 plus x2 times y2 plus so on. Okay, and then you have the summation of the x's, which is literally x1 plus x2 plus x3 and so on. The summation of the y's, which is very similar, y1 plus y2 plus y3 and so on. Okay, and then, sorry, forgot what you guys said. Okay, and then you have the summation. So you have the summation of the x's, summation of the y's, right? And then you have the summation of x squared. So summation of x squared means you're taking x1, squaring it, adding to x2, squaring it, adding to x3, squaring it, okay? Plus, and you continue however many x's you have. So the summation of x squareds is each x is squared and then added together. But then you have summation of x quantity squared, which means you're taking this guy right here, the summation of your x's, and you're squaring that, right? So it's literally the quantity squared of your x1 plus x2 plus x3 and so on. So a lot of different things going on. You need to add all your x's, you need to add all your y's, you need to add all your x times y's, you need to add all your x's squared, all of that. And then to find b, you need the mean of your y and you need the mean of your x. Okay? So if you have all of this down, if not, don't worry, you can always finish watching this video, okay? When I post it. Don't stress out about that, but I do want to finish the lesson, guys. Okay. So over here, right, we have an example. We have the same example as before. 1, 1, 2, 3, 4, 5, and 5, 7. We did this one. I did this one with you guys. Okay. Now we want to find the line of best fit for this data set. And notice we have our grids here. Okay. I don't have one for the summation of x and the summation of y because I can literally just find it right here. So I can do the summation of x, and I can just add all my x's together. 1 plus 2 plus 4 plus 5. I believe that was a 12. Okay. And then you do the same thing for your y's. Okay. So your summation of y's, 1 plus 3 plus 5 plus 7. I believe that was a 16 for us. Okay. And then your x times y's. So you're literally just doing 1 times 1. That's 1. 2 times 3, 6. 4 times 5, 20. 5 times 7, 35. And you need the summation of these. You need these added together. So your summation of your xy's is 1 plus 6 plus 20 plus 35, which is 62. Okay. And then you do your x squareds. Okay. Your x squareds. So this is going to be your x's, each one of them squared. So 1 squared is 1, 2 squared is 4, 4 squared is 16, 5 squared is 25. And then you add those guys. So you have the summation of x squareds. Okay, so that's going to be 1 plus 4 plus 16 plus 25, which is going to be 46. Okay. Now, to find your a, right? To find your a, you need to do the summation of xy minus a fraction where you're dividing by n, but on the top it's your summation of x times the summation of y, so the sum of your y's. Okay, all of this over the summation of your x squareds minus the summation of x quantity squared over n. Okay, and I'll just go ahead and put the b here. Y bar minus a times x bar. Okay, because remember your line of best fit contains the point x bar, y bar, right? So we're using that here to find b. So once you have all of this information, right? I'm gonna zoom out real quick so you guys can see it. Once you have all of your minor information here, you just start plugging in. Okay, so to find a first thing, so big fraction bar. On the top, we have the summation of xy, so that's going to be 62. Minus another fraction bar. At the bottom, you have n, so 1, 2, 3, 4. We have a 4 there, okay? And then we have the summation of x, so that's 12, times the summation of y, that's 16. Okay, that's the top. The bottom, summation of x squared, so that's going to be my 46 right here. Okay, minus another fraction, and at the bottom. But the top is the quantity of your sum of x's squared. So my sum of x's was 12, and I'm going to square that. So you're just plugging in at this point. Now you're simplifying, okay? So all of this, 12 times 16 divided by 4, that's 48. So this becomes 62 minus 48 divided by 46 minus 144 divided by 4 is 36. Okay, keep simplifying that. You're going to get 14 over 10. So your A is approximately 1.4. Or is it exactly 1.4? No, it's exactly 1.4. Your A is exactly 1.4. Okay. So that's your A in your equation. Now you have to find your B, which means you need your Y mean and your X mean. I'm going to do this really quickly. Okay, your X mean is just 12 divided by 4, which is 3. Your Y mean is 16 divided by 4, which is 4. So to find your B, you're just doing your Y mean, which is 4, minus A times your X mean, which is 3. So you do 1.4 times 3 is 4.2. So 4 minus 4.2, which is going to be negative 0.2. So your line of best fit is Y is equal to AX. So A is 1.4 times X. Your plus your B, which is just a minus 0.2. So it's just a matter of going through the process. Okay. It is literally just a matter of going through the process. All right, guys. Nutrition started 2 minutes ago. You are free to go. Sorry for the overing. But we needed to finish this lesson. Okay. Next class, we will talk about, we'll do an activity with all of this. Okay. So we'll be working on an activity next class. All right. Have a good day. Okay. I will see you guys.
Do we have anything to turn in for today?
No. Nope. No homework.